Hello everyone, and welcome to this video called Areas Between Curves. So in this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment that is also called Areas Between Curves. So please understand that this is a preview version of the assignment, and the questions I see in this video may not be exactly the same questions that you see when you work on the assignment yourself. But the objectives should be the same, and the methods for solving problems should be similar. All right, so here I am at Knewton Alta's site. Pardon me. So once again, this is a preview of this Areas Between Curves assignment, which for this particular course is section 6.1. But again, I wouldn't worry about the section number too much, just the material. In the upper right-hand corner, you should see a mastery bar. And this tells you how far along you've gotten in the assignment. Next to that, an activity log. This will show you how many objectives the assignment has. So this has 6 objectives under 3 headings. So we're first going to be on these 2 objectives under the heading Areas Between Curves. And then it's going to throw us into one of the other 2 after that. And we'll stick to maybe area of compound regions and area between curves for functions of y and applications. Then back on the main screen, you have your current objective. Beneath that, a question related to that objective. And at the bottom of every question, you should be able to find a feedback option. So if you notice any issues with the question itself or with the answer explanations after a question, you can send feedback directly to Knewton support, and hopefully someone will get back to you shortly with a way to resolve your issues. You will not find this instructor cheat option. This is for instructors only. But you will find this more instruction option. So if you're working through a problem and you don't remember the material for that objective very well, or need to brush up, or even see it for the first time, open this more instruction option, and you'll be taken to reading to do or videos to watch or both related to that objective, and hopefully having the instruction up will help you get through the problems a little more easily. Okay, so the first objective I'm looking at is determine the area of a region between 2 curves involving transcendental functions. So those are non-algebraic, right? Now, in this heading, areas between curves, we're going to specifically be looking at functions of x. So the y coordinate is determined by an expression involving x. So like here, y equals f of x equals 3 times e to the x minus 1, a function of x, and g of x equals, x squared minus 5. So they're the y coordinate on this curve is the x coordinate squared minus 5. So again, y is a function of x. That's going to be the case for these first couple of objectives. And we're asked, they say here, R is the region bounded by the functions that I just stated. Find the area of the region bounded by the functions on the interval from -1 to 1. They even say here it can be helpful to graph the functions to better determine the correct region. Now, when we're talking about functions of x, like we have here, and then we try to determine, areas between curves. So suppose I have the xy plane here, and we're going to be looking at some region over the interval from x equals a to x equals b, but the region between two curves. So for this particular picture, I'm just going to have a curve, a high curve or a top curve. So say this is y equals f of x. That's going to be the highest curve, the top curve, and then some curve below that. So again, just whatever, just some function y equals, say, g of x. So the region they're speaking of, between the two curves over some interval, right? They gave us that interval from -1 to 1 in the problem. This is the region that I would be discussing. Right, I haven't graphed those two curves yet. I'm just talking about in general here. So again, we'll call this R like they're doing in the problem, right? So there's the region R between the two curves, and we're trying to find its area. So I'm going to set up a little Riemann sum. All right, where remember the setup for areas under just a single curve. So I'm going to break this interval up into n pieces. So again, here we have, say, n subintervals. And the width of each piece would be some little change in x, right? Remember, this is very similar to what we did for area under a single curve to the x-axis. Say delta x here, every single piece here is going to have the same width. It's the length of the interval, b minus a, divided by however many pieces I want to break it up into, divided by n. And then, this left value would be called x sub 0. This far right end would be called x sub n. And then in the ith subinterval, which would look like this, you'd have x sub I minus 1 up to x sub I. We choose x sub I star, right? Just choose some special value in between. So let's say this is the ith interval here. I choose xi star. But now I have two curves to plug into. So this would take me to this point on the lower curve, and then, this point on the upper curve. And I create a little rectangle with a width of delta x, but just the height between these 2 points. Right? We're just only focusing on, we only need to talk about the area between the curves. So this rectangle I just drew here approximates the area between the two curves in this little subinterval. And I would do the same thing for each, for all my n pieces. Now, we know the width. Again, the width of this thing is delta x. The height of it, though, would be, the y coordinate to the top, right, minus the y coordinate to the bottom. Well, the y coordinate to the top, so again, I'll call this y top, is f of x. And the y coordinate of the point on the bottom is g of x. I'll call that y bottom. So we have f of x minus g of x, y to the top minus y to the bottom. That's the height of this rectangle. So then I would do this for, every single piece, right? Create all these little thin rectangles and add them up. So the area of R would be, the limit as n goes to infinity, how I would like the number of pieces to go to infinity, make these rectangles thinner and thinner, get better and better approximations of the sum from, say, I equals, the first piece to the nth piece of the areas of these rectangles, which would be the value of f at xi star minus the value of g at xi star for the heights of them, and then times delta x. Well, this might look familiar, I hope. This limit as n approaches infinity of the sum of a bunch of rectangle areas. Remember, this was the definition of our definite integral. But the integrand this time is not just f, it's this f minus g. So this is the integral from a to b, right, over this interval here. And the integrand would be f of x minus g of x and dx. Right, so this here is going to help us determine, areas between curves. Need the top curve. I need to know the curve that's highest, has the highest y values, minus the bottom curve. All right, top minus bottom, and we integrate over whatever interval they discuss or whatever interval we're given. Now, sometimes we may not be given an interval, but we have to find, where the curved cross to know what's on top, what's on bottom, and what region the two curves bound. But it all ends up boiling down to an integral of a difference of two functions. And we're always going to do top minus bottom so that things stay positive. All right, we're only going to be asked for like the area, the actual amount of space taken up between these two curves, any two curves. So it should be a non-negative value. All right, we're never going to have any negative area. And if you end up with a negative value, that just means you had the wrong curve on top. So let's make it positive, right? Even if you accidentally swap these, you'll just get a negative value instead of, instead of the positive one. So just make it positive to state the area. All right, so that's a brief introduction to that. Now, again, the two curves here. Now I'll draw them by hand as best I can, but also, well, we can look at them in Desmos, right? Nice online graphing calculator. So for this first question, all right, I'm given the following two curves. You got f of x equals, 3 times e to the x minus 1. And then this other g of x. Now, I know I had f was the top one and g was the bottom one on the previous page. That might not be the case all the time. So don't just assume that f's going to be on top and g is going to be on bottom. You have to maybe actually look at a picture, draw it out. That's why they were saying it can be helpful to graph the functions. So g of x is, x squared minus 5. And they want to find the area of the region that's between them that they bound, that's bounded by them on the interval from -1 to 1. So again, I'll do a little hand drawing and see how it compares to the actual graph in Desmos. And you might just want to go to some graphing calculator initially right away, save you a little time. So at -1, e to the -1, that's 1 over e. 3 over e is a little bigger than 1 because 3 is, 3 is a little bigger than e. So that's a little bigger than 1 minus 1. So we have something a little bigger than 0. So at -1, again, you'd have this 3 times e to the -1 minus 1 value. which is again a little bigger than 0, still positive. And then at positive 1, you'd have 3e minus 1. So again, that's between, now e is about 2.7. All right, so that'd be about 8.1 minus 1, about 7.1. So still, that'd be 3e minus 1 at x equals 1 on the other end. And this is just an exponential function. So this is going to rise sharply. And you'd go through the point, 0, 2 and stuff like that, but it's just going to be a exponential base bigger than 1, sharply rising, maybe like this, right? So there's y equals f, right, f of x. And then g of x over here. At negative 1, you get, 1 minus 5, that's got a value of negative 4. So over at negative 1, g is clearly the lower function, the bottom function, and f is the top one. And then at 1, also negative 4. But this is part of a parabola with a vertex at 0, negative 5, right? This is part of a parabola that's opening up. So here's this graph here. So clearly these don't meet. All right, and you can verify that, and again we'll go to Desmos here just to get a better picture, but clearly these do not intersect each other on this interval. So here I am at desmos.com. So the first one they gave me was f of x equals, it was 3e to the x minus 1. And I would like to look at it, just from negative 1 to 1. So remember the little curly braces, put in your condition, negative 1 less than or equal to x, less than or equal to 1. So there's that picture, right? Just that piece of that curve, right? And then g of x was x squared minus 5. Again, I would only like to look at it from negative 1 to 1. Like I said, you get that little piece of a parabola down here. So again, there's that piece of an exponential function up here, piece of this parabola down here. They're clearly not intersecting each other, so we don't have to worry about that. There'll be other problems where we might have to worry about if they cross or not. Because if they cross each other, then the curve on top and the curve on bottom change, and that's going to matter, right, when you're finding area between them. But for right now, right, we're just told to find the area of the region between them over just this interval from negative 1 to 1. So straight up and down at negative 1, straight up and down at 1. Here's this region R that they're talking about. They call this R. What's the area of this space? So remember, with respect to x here, the area of this region is simply going to be, because again, there's no point where they cross each other that I have to worry about setting up a separate integral. We'll get to problems like that later. Got the integral, right? We're going to be adding up the areas of rectangles, little thin rectangles, imagine, from negative 1 to 1. From x equals negative 1 to x equals 1. And again, it's the curve on top. So again, I'll put that y top minus y bottom again. And then with respect to x, so where y is a function of x each time. So here that would be the integral from negative 1 to 1. The y coordinate on the top curve is 3 times e to the x coordinate minus 1. So 3e to the x minus 1. And then minus, so there's the y on the top. The y coordinate, you pick an x value in here. The y coordinate on the bottom curve is that x coordinate squared minus 5. Don't forget parentheses around that. You're going to be subtracting all that. And then, of course, with respect to x, dx representing like the thickness, right? Almost like the delta x. So after distributing the negative here, we get the following. So I'm coming down here with the integral from negative 1 to 1. of just 3 e to the x, and there's a minus x squared. Then I had -1 here, minus -5, -1 plus 5 for +4. And then I'm using the fundamental theorem of calculus part 2, where I state the antiderivative here. So that'd be just 3 e to the x minus 1/3 x cubed plus 4x. And we're going from -1 to 1, where I plug in the upper limit. So that's going to be 3 times e to the first, so 3e. And then when I plug in one of these others, it's going to be -1/3 plus 4. So -1/3 plus 12/3. So that'd be +11/3. So there's the value of my antiderivative at +1. Then subtract from that the value at -1. So I'm going to need to have 3 times e to the -1 power, or 3 over e if you want to write it that way. And then -1 cubed is -1, so this would be plus 1/3, and then minus 4, right? You got 4 times -1. So plus 1/3 minus 12/3, so that'd be minus 11/3 right there. And distribute the negative and combine some stuff. Now 3e, then minus, 3 times e to the -1, those don't go together. This is e to different powers. And then we have 11/3 here, plus another 11/3, so that'd be plus 22/3. And none of these really go together. So here's what I'm going to be entering for the area, and this of course would be area, so they got the words, square units there. That's going to represent the area of this region. Now the nice thing, as you've seen in previous videos, you can pretty easily check the value of a definite integral in Desmos. So I'm back at Desmos here. Now I already have f and g. So I'm going to get rid of those conditions now, so I can actually use them in an integrand. So again, only looking at the area between these, between the x equals -1 and x equals 1. So I'm doing the integral from -1 to 1 of, and then I just did that so I don't have to type them out again. You got f of x minus g of x dx. So again, the function on top minus the function on bottom. And we get this 14.384 blah, 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 right, to 10 decimal places. Well, let's see. The value I ended up with when I did it by hand there, we had 3e minus, 3 times e to the -1, or 3 over e, and then plus, 22/3, and I see I get the same value to at least those 10 decimal places. So again, I'm pretty confident that this is the exact answer. So again, that's what I'm going to be typing in down here, right? The area of that region, this capital A they're talking here, is 3e minus 3, I'll just put 3 over e, that's faster to type, 3e to the -1, and then plus 22/3, and this should be good. Now after you submit an answer, it'll tell you if you're right or wrong, give you some sort of answer explanation. I'd highly recommend reading through the answer explanations, right? If you're correct, maybe they did something in a more efficient way than you did, and you'd like to use that technique for future questions that are similar. Definitely read through these if you are wrong, and hopefully you can figure out where you went wrong and learn from your mistakes. So again, they draw a little picture here of the, f of x up top, g of x on bottom, right? Just from -1 to 1 though only. Again, later on we'll have to figure out where they cross, if they cross each other. But for right now, they just gave us the limits of integration. Wonderful. All right, so this one, instead of transcendental functions, right? So you're not going to have like an exponential or a trig or inverse trig or something. It's just algebraic, just your, powers of variables with, whole number powers, roots, stuff like that. So determine the area of a region between two curves defined by algebraic functions. All right, so remember I said in the last problem, on occasion, you're going to have to figure out where the curves cross each other to determine the area of the region that they are bounding, that they are surrounding. So here R, again, is the region bounded by the functions, this quadratic here and this quadratic here. You got f of x, g of x. So we're asked to find the area A of R, find the area of this region. So again, now notice, right? They did not give us an interval. All right, in the first problem, they told us, over the interval from -1 to 1. Here, we are not given an interval, so that means we have to figure out where these two intersect each other to talk about the region that they are surrounding, the region they bound. So let's do that. So here we got f of x is this, it's 2/3 x squared. There's 2x squared over 3, right? 2/3 x squared plus half x, x divided by 2. And g of x is just half x squared. So notice no interval is given, right? No interval. So if that's the case, right, no interval given, we must find points of intersection. So where are these outputs going to be equal to each other? Right? So where is f of x equal to g of x? Solve this. So that's 2/3 x squared plus 1/2 x. When's this going to be equal to half x squared? Now, if you don't like all the fractions, right, I can multiply everything by the least common denominator, which would be 6. So multiply this side by 6, this side by 6, right? So this would be 4x squared plus 3x equals 3x squared. Then I take everything to one side, subtract 3x squared. This would just be 1x squared plus 3x, equals 0. This is nice and factorable. This is x times x plus 3. So this is equal to 0 when x equals 0 and when x equals -3. So that looks like the interval I'm going to be integrating over here for this region. We'll see the drawing in a second. It's going to be from -3 to 0, right? -3 is to the left of 0. So let me show you. So we're going to go from -3 to 0. These are the x values where these two will meet. Now, at -3, both of them will have a value of 4.5 or 9/2, right? They're supposed to meet. So here's a 9/2. And at 0, they both have a value of 0. Now it's just a matter of, which one is the top one, which one is the bottom one. Now, you could plug in another value in here to determine that. So I'll just do -1 to make it easy. So the value of g at -1 would be 1/2. And the value of f at -1, I'll plot points in a second, would be 2/3 minus a half. That's 4/6 minus 3/6. That'd be 1/6, which is even smaller. So it looks as though f, this is probably a crappy drawing. We'll look at Desmos. But the curve on top, I know it's part of a parabola here. With this is really bad. But the curve on top going through -1, 1/2 there, that'll be g on top. and the curve going from -3 9/2, down to 0 0, but passing through this -1 1/6 will be f, right? F has a lower value than g does. So the region in question, again, this isn't the greatest drawing, but the region in question is this really thin region here. Right, there's R. There's the region in question, very tiny and thin in my crappy drawing there. Yeah, so let me show you in Desmos. That'll be a much nicer looking picture. Right, so, and here is we were given f of x equals 2/3 times x squared plus x over 2 half x, right? And g of x equals just x squared over 2 half x squared. So I'll change the colors up here, red and blue maybe. So you see when you click on them, they do point out where they meet. So you see there's -3 and then the 9/2, right, at -3 4 1/2, and then here's 0 0. So you see the the region between them is again very thin. This very thin little space between the red and the blue curve. All right. So again, the red one's on top, which was G, the blue one's on bottom, which was F. So when I integrate over this interval, I'm going to integrate the difference between, I'm going to do G minus F, top minus bottom, to find this area. So again, the area of this region is going to be the integral. We're going from -3 to 0. It's the y to the top. Pick an x value in here. The y to the top is, the half x squared minus, and then the y coordinate to the bottom curve is the f value, 2/3 x squared plus half x. But you're subtracting all that, right? So I'm going to distribute the negative once again. All right, so let me take this over here. This is going to be then the integral from -3 to 0 of now half x squared, that's 3/6 x squared, minus 4/6 2/3 x squared. So that'd be -1/6 x squared, and then minus half x. And then, of course, with respect to x here, and we're doing fundamental theorem part 2. So antiderivative of this would be -1/18 x cubed minus, and then 1/4 x squared. And we're evaluating these things from, again, -3 to 0. Now, at the upper limit at 0, this has a value of 0. And then at the lower limit, well, when I plug in -3, -3 cubed is, -27, so this would be +27/18 or +3/2. And then minus, and then -3 squared is 9, minus 9/4. And putting these together, this is 6/4 minus 9/4. This will be -3/4, but I'm subtracting this, so, sorry, -3/4, right? 6/4 minus 9/4. So -3/4 in here, but it's being subtracted. So the area of this region is positive, 3/4. It's 3/4 of a square unit in between those two curves in that thin little region. Now, let me double check that again by integrating in Desmos here. Integral from, we went from -3 to 0. And again, I have my g of x and f of x already up. So we had g was on top, minus f was on bottom, dx, and there's, there's 3/4, 0.75, change to a fraction there, 3/4. So that's what I'm going to enter. So the area between them. Now 0.75 is exact, that the decimal ends. So they're 0.75 square units, 3/4 square units, same thing. They draw a very slight thin area there. Less than a square unit taken up by all that space. All right, so this is more with algebraic functions once again. So again, I'll do the same where I'll try my best to draw the region. We can look at it in Desmos. And, another one where they didn't give us an interval. All right, they didn't say find the area between these two, bounded by these two functions over a specific interval. So I have to figure out where they meet. All right. So here we're given f of x equals the square root of 2x minus 1, and g of x is 2/5 x plus 3/5. So again, no interval is given. So going to figure out where they cross, right? So solve this equation here. Where is f of x going to be equal to g of x? So where is the square root of 2x minus 1 going to be equal to 2/5 x plus 3/5? Now, if you'd like, you can multiply everything by 5. Put the 5 over here with the square root. And then you would just have 2x plus 3 on the right side. And then you would square both sides to get rid of that square root, Now, this would be 5 squared times this. So you got 25 times the quantity. 2x minus 1, right? Squaring gets rid of that square root. Don't forget the parentheses around that radicand, Then over here, you got to do 2x plus 3 times 2x plus 3 and FOIL. This would be 4x squared. All right, 2x times 2x. Then you have 2x times 3, but twice, so 6x and 6x for 12x plus 12x, and then 3 times 3 is 9. And now I have a quadratic to solve. Distribute the 25 here. So we now have 50x minus 25 equals this, 4x squared plus 12x plus 9. Take everything to this side over here, get 0 on one side. So we got 0 equals 4x squared. Now 12x minus 50x, that'd be negative 38x. And then I would add 25. 9 plus 25 is positive 34. And then I notice that all these coefficients here are even, so I'm going to divide everything by 2 now to shrink the numbers up a bit. So we got 2x squared, 0 equals 2x squared minus 19x plus 17. And right there, 2 and 17, when I multiply, this is factorable. Or I can do that AC method. 2 times 17 is 34, and negative 2, negative 17 add up to negative 19. So I could factor this thing. This will factor to x minus 1 times 2x minus 17. Right, because you FOIL, you got 2x squared minus 2x minus 17x for the minus 19x and then plus 17. So the two values are 1 and 17 halves. All right, 1 and 17 halves. Okay, now when I go to my graph, again, I'll do the best to draw this region. We'll look at it in Desmos too. So we're going from now 1 will be to the left of 17 halves is 8.5. So that'll be to the right of 1. And then both of these will be at when x equals 1, y equals 1 for both of these. And when x equals 17 halves, this would be 17/5 plus 3/5, that's 20/5, that's 4. Or you have the square root of 16 in this one. Either way, at 17 halves, they both have a value of 4. And then g of x is just a straight line, right? This is a linear function. So this is g. And then this is your square root function with something with a positive coefficient in it. So this is going to be going up higher. Now you could do the same. This is going to be the top function. Something like this. Going from 1, 1 to 4, 4 here. There's f on top, g on bottom. Now you could have plugged in a value in between, say 5 would be nice, I guess it really doesn't matter. Plug in 2. This would be the square root of 3, which is about 1.7 something. And this would be 7/5, which would be about 1.2, right? This would be bigger. F would be bigger. All right, so the region being discussed, is this region here. This is the R. All right, this little thin area between. So just to doubly verify this, right, we're gonna go to Desmos. Let's look at the drawings. So again, my f function, f of x was the square root of 2x minus 1. G of x, just, 2x over 5, 2/5 x plus 3/5. And you see how the green curve is above the purple curve, and they meet at 1, 1 and 8.5, 4. That was your 17/2, 4. So you see this little thin white space between them. That's what we're trying to find the area of. So I'm going to be integrating again from 1 to 8.5 to 17/2 of, and then this is going to be f of x minus g of x. Right, f is on top, and this is actually a nice fraction here, 2.25, 9/4. So that's what I'm going to enter. All right, now you could do that by hand, right? Do f minus g, but we've done a lot of integration in previous videos, so I'm not going to do a lot of these if I realize they're going to be rational. Now a lot of these algebraic functions, I'm not saying all of them are going to be, but I recognize that when you plug in 1 here to the square root of 2x minus 1, you get a rational number. When you plug in 17/2, you get a rational number, and this is a line, so I figured it would be a rational value, right? 9/4, 2.25 square units in between. Great. So again, they do the same thing. They actually go through, take you through the integration, right? Okay. But you see the little picture here with the thin region between. All right. So another one where now one of these, neither of these are transcendental. This is a rational function with, polynomial over polynomial, and this is a line. Either way, I think it might be because you're going to have a logarithm when you do the antiderivative. So that's why the word transcendental, that's why this is in this transcendental one. Okay. Yeah, the functions themselves are not transcendental, but when we do the antiderivative of f, it'll involve a logarithm, which is transcendental, right? Not algebraic. So anyway, now notice here, they tell us, to integrate over a specific interval. So again, I can make the best drawing of this that I can. And I don't think these are going to meet. Or just go to Desmos. You can do them by hand, but let's just go to Desmos. You're at home, you'll be able to do this, right? You got f of x equals, it was 7 divided by, x minus 1. It was negative 1 plus x, which is the same thing as x minus 1. So there's f, and then here's, g of x was just a straight line, x minus 7. And from -4 to 8, now look at, they meet at 8. Oh, not -4 to 8. I was like, just 4 to 8. Good. I was like, -4 doesn't make any sense. So yeah, so from x equals 4, so I'll put in x equals 4 here. You see a straight line. So you see this little, it's almost a triangular shape, All right, they meet at this point 8, 1. Here's x equals 4. So it's this little like triangular, almost triangular, right? It's not a perfect triangle. This is more slopey. Right? It's not a line, not a segment. But we're finding the area of this. Now in this region from 4 to 8, right? From x equals 4 to x equals 8, the red curve f is on top and the blue curve g is on bottom. Now here if I integrate, do the integral from 4 to 8 of, again, f is on top, g on the bottom, f of x minus g of x dx, it's not going to be a nice value because the antiderivative of f will involve a logarithm. So I've got this at least, and we can check it later when we actually do this. So I'm actually do this one by hand. All right, the integral anyway. I'm not going to draw the picture again. So we have the integral from, it's from 4 to 8 of, now the function on top was that f function, which was 7 over x minus 1, and then minus, the g function was on bottom, which was x minus 7. And then, of course, with respect to x. So fundamental theorem part 2, now this first one is just going to be 7 times the natural log of the absolute value of x minus 1. All right, easy enough. Take the derivative of this, it'll be this. Right? And then this, I can consider a linear as a whole here. This is just with a coefficient of 1 on the x. So this is simply going to be minus half of x minus 7 squared. And again, you can take the derivative of this, chain rule and all that. You're just going to get 1 times x minus 7. And we're going from 4 to 8. So I plug in 8 first. So this would be 7 times the natural log of the absolute value of 7, which is just 7, right? So there's no need for absolute value around that. Then minus a half, right? Because 8 minus 7 would be 1 squared is 1, so there's minus a half there. So there's the value of this integrand antiderivative at 8. Then we're taking away the value of this thing at 4, which would be 7 times the natural log of, the absolute value of 3, but that's just 3. And then 4 minus 7 is negative 3, but squared is 9, so this would be minus 9 halves. And we get, after distributing this minus here, putting some like stuff, we got 7 times the natural log of 7. And minus, 7 times the natural log of 3. And they have negative half, and then plus 9 halves. Negative 1 half plus 9 halves. That'd be positive 8 halves, or plus 4. So this should be good. Now you can use properties of logarithms to rewrite this if you want, but this should be good for the value, and let's double check that. So I'm on Desmos here. I'm gonna enter what I just got. 7 times the natural log of 7 minus 7 times the natural log of 3, and then plus 4. And you see it's the same as my integral statement from earlier. Same value to at least those, looks like 11 decimal places. So it definitely giving me confidence that this is the correct exact value. So again, 7 times the natural log of 7 minus 7 times the natural log of 3 plus 4. Okay. So again, the picture of the region, like I showed you, I mean, again, I didn't highlight that and shade it in, but I had x equals 4 up and showed, it's almost like a triangle, but not exactly because of this little curvy part up here. All right, so more algebraic. So once again, we don't know where they meet. I'm just going to put them in Desmos. All right, we've already seen a couple where we have to find it ourselves, but the nice thing about Desmos is when I put both these in and you click on one of the curves, you'll be able to see where they meet. So our two functions this time, actually zoom this out a bit. So the two functions this time, you got f of x is 4 divided by x, so that curve, and g of x is another line, negative 2/5, 2x over 5 plus 22 fifths. G of x equals negative 2x over 5 plus 22 fifths. So you see they meet when x equals 1 and when x equals 10. And then the region in between them, the g is the top function, f is the bottom. So I'm going to be integrating from 1 to 10 of, g minus x, right? Again, top minus bottom for these areas with respect to the x-axis. Now again, this is, the antiderivative of f will involve a logarithm. So that's why this isn't a nice number. So again, going to go do that by hand real quick. So the integral I set up, again, was the integral from, they met at x equals 1, and then they met again at x equals 10. So the integral from 1 to 10, and g, the line, was the top curve, so negative 2/5 x plus 22 fifths. This was the y coordinate to the top curve, then minus, I guess all this in the grand here, and then minus, and then, the y coordinate to the bottom curve, the f curve, was just 4 over x, and dx here. So again, fundamental theorem part 2, it's a nice sum already. So this would be negative 1/5 x squared plus 22 fifths x, and minus 4 times the natural log of the absolute value of x, right? Remember the antiderivative of 1 over x was natural log of the absolute value of x. But we got 4 of it there. And then we're going from 1 to 10. So when I plug in 10, now 10 squared is 100 times negative 1/5 would be negative 20. Again, 10 over 5 is 2 times 22 is 44. So then you got plus 44. Then minus 4 times the natural log of the absolute value of 10 is just 10. So again, this is 4. So there, and then these two can be put together. This is positive 24. All right, so the value at 10 is 24 minus 4 times the natural log of 10. And then we're taking away from this the value at 1. Well, that would just be negative 1/5 plus 22 fifths. All right, so that's 21 fifths. And negative 1/5 plus 22 fifths. And then, minus 0. Remember, the natural log of 1 was 0. So that's all you got there. And 24, when you multiply by 5 over 5, that's 120 fifths. Take away 21 fifths. That is, 99 fifths. So when all's said and done here, you put these together, you got 99 fifths. And this, minus 4 times the natural log of 10 term as well. So this is what I'll enter. Now let's double check this. Make sure it has the same value as the integral I set up in Desmos. So I had, 99 fifths minus 4 times the natural log of 10. And look at that. It's the same value to those 9 decimal places. So feel pretty good about that. So again, we got 99 fifths minus 4 times the natural log of 10. Great. Same thing, drawing the picture there of the area. Okay. So here they just give us 2 lines. And they give us an interval. All right. So again, I'll draw these and we'll put up x equals negative 3, x equals 0, and we'll get an idea for the region in question. So the f of x function was 3 halves x minus 4. So 3x over 2 minus 4, the g of x function was just negative 5x over 3, negative 5/3 x. And we're looking at the interval from x equals negative 3 to x equals 0. So just this little trapezoid here, I don't know if you can see that, but so from this point to this point to this point and this point, right? Those are the four corners of my that's a little trapezoid. Now, because it's a trapezoid, I mean, I could find the area of this region without doing too much work. Remember this one base from negative 3, 5 to down here? That's 13.5 units long, and then from 0, 0 to 0, negative 4, that's 4 units long. So add those up, and you got 17.5, which would be 35 halves. Cut that in half would be 35 fourths. Then multiply by the distance between these two bases here, which would be 5 units. So 35 fourths, times 5, 150 plus 25, 175 fourths, 175 fourths. Now, in this region from negative 3, oh, sorry, these are 3, no, 175 fourths, sorry, 35 times 3, 35 fourths times 3, that'd be 90, 105 fourths. Still, in this region from, from x equals negative 3 to x equals 0, pretty sure it was x equals 0, yeah, negative 3 to 0, the red curve, the red line is on top, the black line is on bottom, so g is on top, f is on bottom. So I can just set up the integral. All right, let's just do that where I got the integral from, negative 3 at the lower limit to 0 for the upper limit. And again, it was g on top, g of x, I called it already, minus f of x on bottom, dx. And look, there's 26/25 or the 105 fourths as I mentioned earlier. So that should be the area of this trapezoid region. So 105 fourths square units. So they probably have, and again, they shaded in down here, this trapezoidal region. All right, so this is pretty similar. Oh, but they just want us to set up the integral. Don't need to simplify. Okay, so the left limit is negative 1, the right limit is 3, so I'll put the lower limit negative 1, upper limit 3, and then it's just a matter of knowing which function's on top. Now, at negative 1, this value of f would be negative 5.5. The value of g would be 9 fourths minus negative 5 fourths. So f is lower. So it would be g minus f. So in the parentheses here, I can put, g first, right? G is the top function, 9x over 4 minus 3, and then minus, and then f is the bottom function, negative x over 2 minus 6. And that should be good, as long as you have top minus bottom. Great. So they actually simplified the expression, right? They actually subtracted these and put them together, get 11x over 4 plus 3. But as long as what you type in is equivalent to what they have, right? So all I needed there was the limits and what's the curve on top minus the curve on bottom. So I'm going to draw a picture of it here. All right, so this one is a triangle, not even a trapezoid. So here's an interactive one where now I gotta, move some points around. So look, the interval being given to us is from negative 7 to 2. So I got to move these lines here to negative 7 on the A and positive 2 on the B. And then just make sure we're plotting the curves. Now at negative 7, the value of f would be 4. So there's f of x up here. So negative 7, 4 on the left end. And at 2, it would have a value of negative 5. All right, so 2, let's move this to 2, negative 5. There's the graph of f. And then this g function, again, I really just need to plot some points. It'd be really easy if I plugged in values of x that were multiples of 3 here, because you got this denominator of 3. So at like -6, that would be 8 minus 7 would be 1. So I'll move one of these points to -6, 1. All right, there's -6, 1 there. And, another one, let's go -3. Or 0, right? 0, -7. Oops, wrong one, wrong one. This is g. So here's 0, -7. So I got the f curve, again with -7, 4 on one end, 2, would be 2, yeah, 2, -5 on the other end. And then this g function, because the value at the ends wasn't a nice whole number, I just found ones where the input was a multiple of 3. So again, -6, -1, and 0, -7. And there's a picture of the region, and that's all we're asked to make here. All right, just drag these points around, move f and g around in the interval and the endpoints of the interval to kind of highlight the region bounded by all these curves. All right, great. All right, so another one where we're given an interval. So again, I'll draw these. Now make sure you're in radian mode. Don't forget when you're working with the trig functions in calculus here. So one of these functions is 1 minus 3 cosine x. The other one is 4 sine x. And we're only looking from 0 to pi over 2. All right, so I'll do something similar here back in Desmos. So one of them was f of x is 1 minus 3 cosine x. And in radians, g of x is just 4 sine of x. But just from 0 to pi over 2, x equals 0, x equals, pi over 2. So just this little region here between the green and blue line. So you see how in this region, red's on top, black is on bottom. So g's on top, f is on bottom. So this area is going to be the integral from 0 to pi over 2 of, again, the red's on top. So that was the 4 sine x. So 4 sine of x minus, and then the g, or sorry, the black, the f was on bottom, 1 minus 3 minus the quantity 1 minus 3, or 1, yeah, it's 1 minus 3 cosine x, yeah, 3 cosine x and dx. So this is, again, not a very nice number. All right, so let's actually find this by hand and verify that we indeed get the same value, just making sure my functions are correct. So again, it was for this integral here. We have the integral from 0 to pi over 2 of, and then the 4 sine x curve was on top, minus, and then the quantity 1 minus 3 cosine x was on the bottom with respect to x. Now I'll distribute the negative here, and that'll be minus 1 plus 3 cosine x. All right, now it's a nice sum. Do antiderivative term by term. So this fundamental theorem of calculus part 2. So this would be -4 cosine x minus x for the -1, and then plus 3 sine x, right, when I'm doing antiderivatives. And we're going from, 0 to pi over 2. Now, when I plug in pi over 2, so remember cosine of pi over 2 was 0. This would be just negative pi over 2. And then sine of pi over 2 is 1. This is plus 3. So 3 minus the pi over 2 for the upper limit, plugging in the upper limit. And then plug in 0. Now the cosine of 0 was 1. So this is -4. minus 0 plus 0. Right, so this is plus 4. So this ends up being 7, right? You got 3 minus negative 4, 7 minus pi over 2. That should be the same value as what I got here in Desmos. So let's double check. 7 minus pi over 2, and yes, that's the same to that many decimal places. So should be our exact value for this area. 7 minus the pi symbol in the keyboard here, pi over 2 square units. Cool. And again, there's a picture of the same region. I kind of, again, I'm not shading in Desmos, but they're shading it in for us. All right, so another very similar one. In fact, I think it would be exactly the same, but you just got 2 sine instead of 4 sine. The f function's the same. So all they did was change 4 sine to 2 sine. So you see, that'll still be the top curve here. It's still the curve on top, the red curve, the 2 sine x. Yeah, so that would not a whole lot changes, right? All that would change is this becomes 2 sine. So this would be negative 2 cosine, and when I plug in pi over 2, again, this would be 0, and then negative pi over 2 plus 3 still. And then when I plug in 0, this would be minus, negative 2. So instead of 7 minus pi over 2, it's going to be 5 minus pi over 2. That's all that's going to change, right? Change this to 5, and you see the exact same value for that integral, this describing the area between them. So yeah, it was the same limits, right? 0 to pi over 2. Good. So 5 minus pi over 2 square units. Great. Again, same kind of picture there, showing the region. Okay, so now we're into another heading, right? Those first two objectives were just the area between curves. So now we're in this heading, the area of compound regions. So in the first two objectives, every single graph we were looking at, every single region, right, we were finding the area of. The curve on top and the curve on bottom never changed, right? It was always the same curve on top and the same curve on bottom. So in these two objectives with these compound regions, the curve on top and bottom will switch. So we have to determine where these things meet, right, where they cross, so that way we know when to switch the integral, when to turn it, when to change, at what value do we need to change the function on top minus function on bottom. All right, that's a compound region. You'll see when we look at the first picture here. Oops. Wanted to go to the problem. The problem. There. Okay. All right, so here, find the area A of the region that is bounded between the curve. You got f of x equals the natural log of x plus 1, and the line g of x equals negative 4x over e plus 6 over the interval from 1 to 4. So watch. All right, so I'll graph this as best I can by hand. We'll look at it in Desmos. So you're going to see these meet at the value e. It's not really, you really couldn't figure that out by solving an equation because one's a log and one's a linear. You really did never in pre-calculus or algebra before this, unless you were at some sort of advanced school. You didn't really talk about solving equations involving both linear functions and polynomial functions. But my graphs here, f of x equals the natural log of x plus 1, g of x is a negative 4 over e times x. So that's the slope of the line, some weird slope there involving e, plus 6. And we're on the interval. They're asking us to find the area bounded by these curves, between these curves, between x equals 1 and x equals 4. All right, so watch. So at x equals 1, so again, we're going 1 to 4. Natural log of 1 is 0, plus 1 is 1. Okay, so you got natural, is 1, 1 on the graph of f. Then the natural log of 4, and e to some power is 4. It's 1 point something, so this is 2 point something. So again, let's say there's the natural log of 4 plus 1. I don't know exactly what that value is. I just know it's going to be 2 point something. And then here's, the f curve, right? It's natural log, so, curling up like this. And we'll look at it in Desmos in a better picture, but there's f. Now g, and at 1. Now negative 4 over e, again, e is about 3, a little less than 3. So this is between negative, this is between negative 4 halves and negative 4 thirds. So between negative 2 and negative 4 thirds, negative 1 and a third. So then adding 6 to that, this is going to be between 4 and, 6 minus 1 and a third, 4 and 2 thirds. So something between 4 and 4 and 2 thirds. So again, that's going to be definitely higher than 1. So again, here the graph of g at 1 is going to be higher than f. But then at 4, now look, you can compare them. Again, it's tough to compare, but it's a line with a negative slope. Now it could be negative and not get below f, but again, at e, all right, this is just something that looking at these two, it's gonna be, you don't set these equal to each other. You're not going to be able to solve with like normal methods, but just like eyeballing these. E, now remember E is about 2.7. All right, so let's say that's here. That's definitely between 1 and 4. When x equals E, right, natural log of E is 1, 1 plus 1 is 2. And then E over E is canceled. You got negative 4 plus 6 is 2. So they meet at the point E2. And then again, I got some, and this is a line with a negative slope. So it's going to cross at this point E2, and there's G. So the region they're talking about, they want this area, right? They want the area between the curves from x equals 1 to x equals 4. So this little bow tie region, right? They want this area and this area as well. But you see how from 1 to E, the top curve is G, the bottom curve is F. And then from E to 4, the top curve is F, the bottom curve is G. So I got to split this up. That's what they meant by compound regions, right? There's two, I'm going to have to set up multiple integrals, break it up to find the area between the curves. So the area, and I'm doing from 1 to E first. You got the integral from 1 to E, and in that interval, top curve is G, so the negative 4 over E times x plus 6, minus, and then the bottom curve is the F curve, this natural log of x plus 1. And all that is the integrand dx. And then we're going to add to that, right, plus. So again, this, so let's call this, say, region number 1. And then this other one we'll call region 2, R2. So you see the next integral I add will be the integral from e to 4 of, and then the other way around, right? Where f is on top. So this natural log of x plus 1 is on top, minus, and then the g curve, the line, is on the bottom, negative 4 over e times x plus 6. All right, so I got to find each of these separately. Now, I mentioned this earlier. If you mess one of these up, again, you got to figure out where they cross to figure to set up the integrals properly, right? Set up the limits correctly. But if you accidentally switch the top and the bottom, you'll just end up with the opposite value. So if I accidentally put, you know, g minus f here again, I'll just get a negative number. Just make it positive. Just make it positive. Talk about the area between them. So the key here is to figure out where they cross, right? They cross at E. So at E, I got to split up my integral and then add them up. All right, so let me distribute the negatives on these, and we'll work on these on the second page. All right, I know I said I'd go to Desmos here, but you get the idea of this little bow tie region. All right, so for region number 1, again, this is the integral from 1 to E, where you got, negative 4 over E times x. Then I got minus the natural log of x. And then you got 6 here, minus 1, so that'd be plus 5 with respect to x. So let's find this area. So fundamental theorem of calculus part 2. So with this just x to the first here, this would be negative 2 over e times x squared minus, there was a video I had put out a little bit ago, again, maybe depending on when you're seeing this, where I went over this is a Calc 1 course, so usually they're introducing you to the integral of natural log in a Calc 2 with 5 parts or whatever, but we were shown the formula in Calc 1 in a video I did called Integrals Involving Exponential and Logarithmic Functions. So remember, the antiderivative of just natural log of x was x times the natural log of x minus x. Right, that whole thing is the antiderivative, the basic antiderivative of natural log. And then you got plus 5x. And then we're going from, 1 to e. Now, if you distribute the negative here, you can make this plus 6x. So I could have negative 2 over e times x squared, and then minus x times the natural log of x, and then plus 6x. And I'll bring this back because we're just going to have the opposite of that, right? This is just the other order when I do the integral from e to 4. So I'll keep this in mind. Now when I plug in e, and e squared over e here would just be e, so you got negative 2 times e. Natural log of e is 1 minus e, so this is minus e times 1 or just minus e, and then plus 6e. So all said and done, the value of this thing at e is 3e, right? And it's negative 3e plus 6e minus, and then the value of all this at 1, you got negative 2 over e, natural log of 1 is 0, and then plus 6. But, this is being subtracted, all this, so we end up with 3e plus 2 over e minus 6. All right, so that's, oh, sorry, 3e plus 2 over e minus 6. So this is the area of this first region, right? This just from 1 to e here, where g is on top, f is on bottom. So then I'm going to do the same thing for R2, right? This second region from e to 4. So I got the integral from e to 4 of, and it was, f minus g, right? Top minus bottom was f minus g. So this f function, natural log of x plus 1, minus the g function, negative 4 over e times x plus 6. But like I said, this is just the opposite of the order I had it in up here. So we're just going to get the opposite, antiderivative. So this will be, positive 2 over e x squared, and then plus x times the natural log of x. Well, absolute value of x, but these are all positive numbers anyway. And then minus 6x. Right, again, just the opposite of this one I got earlier when I had it in the other order. And we're going, e to 4. When I plug in 4, this is a 16 times 2, that's 32 over e plus 4 times the natural log of 4, and then minus 24. All right, so there's the value at 4, minus, and then we already found the value at e. Right, we did that here earlier, but again, it's going to be the opposite. Right, when we plugged in e to this one earlier, it was 3e. So when I plug in e to this one, it's just going to be the opposite, so it'll be negative 3e. And you're subtracting that, so that'll be plus 3e. So yeah, so we end up with a 32 over e plus 4 times the natural log of 4 minus 24, and then plus 3e. Okay, and then we're putting these together. This, right, this earlier was the area of the first region from when I was integrating from 1 to e. And then this here is the integral that sets up the area of this region from e to 4. So I need to put these together. We're going to add these, right? So we'll put a plus sign here. So I add these up, combine like stuff, so the total area involved, right, the area of the regions in between those two curves. Let's see, I got 2 over e plus 32 over e, that'd be 34 over e. There's 3e plus another 3e plus 6e. Got that and that and that and that. And then there's still this, plus 4 times the natural log of 4. Got that. And then the two constants, negative 6 and negative 24, added together make minus 30. So this is our, exact value, the area of this little bow tie region I got here, both of those put together in exact form. And you can set up the integrals in Desmos and check them out, but I'm pretty confident that I did this correctly, and I'm really hoping I did. So I enter an exact answer. So we had 34 over e plus 6e plus 4 times the natural log of 4, and then minus 30 square units. Right. And they're drawing it again. This again, the little bow tie region there. So again, you got to figure out where they cross, so you know when it switches from one on top to the other on bottom, and then setting up two integrals. Right? They call them A1. I was calling them R1 and R2. They're saying A1 and A2 again from 1 to E to 4. Yeah, the key is to figuring out where do they meet, where do they cross. All right, so there's another one. Now look, they give us the picture here. They give us the region and find, we have to find the area. So g is a line, just x minus 5. So this red curve is the g function. And f is this bluish curve, the negative 5 plus 8 over x squared. So again, the red is f, the blue is g, and then the one on top the whole time So you see the curve on top doesn't change, but it's the curve on bottom that changes. The curve on top is just y equals 3. So for both of the regions here, I'm going to have 3 minus, but then the thing I'm subtracting is different. For at x equals 2, you see how at x equals 2, the blue curve changes to, it goes from having the blue curve on bottom to the red curve on bottom. And they meet up here at 1 to 8. So we got the integral from 1 to 8. We're going to start off from 1 to 2, do 3 minus f, integrate that. And then from 2 to 8, got 3 minus g, and integrate that. But that's just a triangle. So I'm just going to do the 3 minus f integral from 1 to 2. And then this triangle here has a, negative 3 to 3, 1 base 6 and height, that's from 2 to 8, 6. So that's a 6 base 6 height. This is an 18 square unit triangle. So I'm just going to do the 3 minus f integral from 1 to 2 and then add 18. Right, because there's 18 square units in that triangle from 2 to 8, where you got 3 minus g. So again, just over the interval from 1 to 2. Y equals 3 was on top, and y equals f, this negative 5 plus now 8 over x squared, I'm going to rewrite as 8 times x to the negative 2. So there was y equals 3 on top, and then y equals this, negative 5 plus 8 over x squared on bottom. But just from 1 to 2 this is happening. So this will give us this area, and then again, plus we're going to add that 18 square units. This was from 2 to 8 with y equals 3 on top and y equals x minus 5 on bottom, but that just gave me a triangle with base 6, height 6. So that's why I got plus 18 here. All right, so distributing this negative, you got 3 minus negative 5, that's 3 plus 5, that's 8. And then minus, 8 times x to the negative 2. So we're integrating this. So that'll just be 8x, and then plus, 8 over x, right? 8 times x to the negative 1. To be x to the negative 1 times negative 1. And then we're going 1 to 2. Now when I plug in 2, that's 16 plus, 4. So that's 20. And then when I plug in 1, that's 8 plus 8, that's 16. So this all together is 4, and they got plus 18 later for the triangle. 4 for the first region from x equals 1 to 2, 18 from 2 to 8 for that triangle. Put it all together, that's 22 square units total. So a nice number there. Right. So yeah, I wonder if they don't break it up. But you see how they break it up though? So they got 2 to 8 for that. Turns out to be a triangle, and then 1 to 2 with the y minus f. 3 minus f. Right, no picture here. So once again, it's going to be nice to figure out where these cross, and it looks like that's going to be at 1, at x equals 1. Both of these will be at the point 1, 0. So again, the two functions here, f of x is this exponential function, e to the x minus 1 power, then minus 1. G of x is a simple linear function, 2 minus 2x. I'll say, now you don't have to solve this, right? Again, this says exponential, this is a linear function. Probably haven't seen how to solve anything like that, and unless you were introduced to the W function, right? Whatever. I'm not going to get into that, but So this happens though at x equals 1, right? Again, it's hopefully they give it, like the last one where it was a log and a linear function. Hoping it's pretty obvious when they're going to meet, right? When x equals 1, this would be e to the 0, which is 1 minus 1 is 0. And then when x equals 1 here, 2 minus 2 is 0. So they both meet at the point 1, 0. So this point here is where they cross. And we're looking at the interval from -1 to 3. Now I just need to figure out, which one's above. Now, honestly, again, as long as you figure out where they cross. Look, you don't even need the picture. If I do the integral from -1 to 1 first, right? I would do the integral from -1 to 1 first, because then from 1 to 3, what's on top and what's on bottom is going to switch. Now, say I just did f minus g. So e to the x minus 1, then minus, 2 minus 2x. I'll distribute this. So this will be e to the x minus 1, and then minus 1 minus 2, so minus 3, and then plus 2x. Do my antiderivative. This will be e to the x minus 1 minus 3x plus x squared from -1 to 1. And then when I plug in 1, got e to the 0, which is 1, and then minus 3 plus 1. All right, that's the value at 1, which is just negative 1. Right? Minus value at -1 would be e to the -2, so 1 over e squared, right? Tiny number, about 1/9 or so. And then plus 3, and then plus 1. So when I distribute the negative here, again, this is just plus 4. And this is -1 altogether. So I'd end up with a negative value. -1 minus 4 would be -5, and then minus 1 over e squared. So you see I ended up with a negative. Just take the opposite. All right, so you don't need to know what's on top, what's on bottom, just where they're going to cross, though. You got to know where they intersect. You got to know that value. So the area of the, if you were to look at the graph, the area of this first region is going to be +5 plus 1 over e squared, or e to the -2nd. Okay, that's going to be the area of the region between the two curves, from -1 to 1. Now that tells me that, I had f on top, g on bottom, but it should have been the other way around, g minus f. So when I do from 1 to 3, f minus g should be the correct top minus bottom. So the integral from 1 to 3, and I'll do the same thing where I do f minus g here, and this should give me a positive value. Well, again, it's just this. And it's just this, e to the x minus 1 minus 3 plus 2x again. And it's the same antiderivative as I got earlier. So e to the x minus 1 minus 3x plus x squared. But this time we're plugging in, 1 to 3. Now when I plug in 3, this would be e squared minus 9 plus 9. So it's just e squared at top. And then I plug in the bottom limit. Again, we already did the value at 1 earlier. That's -1. So this is e squared plus 1. And that's a positive value, right? So the area between the two curves here, I'll call this A2. The area between the curves from x equals 1 to 3 should be e squared plus 1. And then we add these. So the total area is going to be, 6 plus e squared plus 1 over e squared, or e to the -2. That should be the total area between the curves without even drawing them. And the key is to figure out where they're going to cross. And if you end up with a negative value for an area, just make it positive, right? Take the opposite like I did. So you got 6 plus, e squared plus 1 over e squared, or e to the -2. So you see the drawing, see how g is on top and f is on bottom to the left of 1, but then f is on top, g is on bottom to the right of 1. Okay. All right, so here's another one where it says that's bounded above. So this curve's got to be on top, and the line 3 minus x, and bounded below by the x-axis, right? So yeah, I gotta draw this one. This one's a little trickier. There's three curves they mentioned there. They have F, they have G, and they mention the x-axis also is going to be part of this. So again, F is this quadratic. G is a line, 3 minus x. And they said the x-axis is going to be the below curve, bounded below. So let's draw these, right? Now first we got to figure out where they meet. They'll meet at -1. That's one of them. So again, let's take x minus 1 squared. Now this will be a nice quadratic. X squared minus 2x plus 1. When's this equal to 3 minus x? So x squared, plus x, sorry, minus x, and then minus 2. And this factors to x minus 2 times x plus 1. So yeah, they're going to meet at -1 and 2. So at -1, they're both going to have a value of 4. And at 2, they both have a value of 1. And, one of them's a line, straight line. So here's the g function. That's g. F is a parabola, right? It's just y equals x squared, but move to the left one. So, oh, sorry, move to the right one. So 1, 0 is the vertex for that. And here's that graph. Yeah, there's F. Yeah, that's a pretty faint marker. Yeah, these have been out too long. So again, here's F on the bottom there. So it says, okay. All right. So it says so we're not finding the area between the two. So read it again. A little trickier, this one. It says the area of the region that's bounded above by this curve and this line. So the curve and the line would both be on top. So I keep going with the line. So now, where does this line hit the x-axis? That would be at 3, right? 3 minus x would be 0 at 3. So there's 3, 0 here. So this curve, this parabola, and this line are on top, and they say it's bounded below by the x-axis. So the region they're talking about here, and the x-axis is this, the region they're talking about then is this, not this. This, right? It's bounded above by these two curves. F and G are are the top curves, and bounded below by the x-axis. So this is the region that we're talking about. When you see at x equals 2 here, at x equals 2, the curve on top in this region changes from F to G. But the curve on bottom is still y equals 0 the whole time, right? That's the x-axis. So this area is just going to be the integral from 1 to 2 of just the area under F. So just the area under x minus 1 squared with respect to x. So that'd be 1/3 times x minus 1 cubed. All right, we're going from 1 to 2. When I plug in 2, this would just be 1/3 minus 0. So that's 1/3 of a square unit here. And we're going to add to that the area from 2 to 3, the integral from 2 to 3 of just the area under g to the x-axis. So that's the integral of g, the integral of 3 minus x dx. So that would be 3x minus half x squared, and from 2 to 3. Now when I plug in 3, that'd be 9 minus 9 halves, 18 halves minus 9 halves, that'd be 9 halves. All right, 9 minus 4.5 is 4.5 again. Then minus, and then 6 minus, and then half of 4, 6 minus 2, so 4. But 9 halves minus 8 halves, that's just a half. So we get a third plus a half, 2 6 plus 3 6 for 5 6 total. This little purple area I shaded here has a total area of 5 6 square units. So again, that was a little trickier by the way they're worded, right? Bounded above means that the curves they're giving us are on the top. Bounded below means that that should be on the bottom, right? So 5 6 square units total area for that region. Again, they'll show you here. See, it's that region, not the area between the red and the blue here, but the blue and the red are, bounding the region above, the x-axis bounding it below. So reread carefully. All right. So this time, again, what's the area just between the two curves over this interval from pi to 2 pi? So 4 sine of a fourth x, and then g is 4 times the sine of half x. All right, so this time I'm just going to look at them. Gonna make sure you're in radian mode when graphing trig functions here. So one of these, again, f of x was 4 times the sine of x over 4. The other one was, g of x was what? 4 times the sine of half x. So x over 2. And we're only looking at from x equals pi to x equals 2 pi. So between these two vertical lines here, the green and purple, now look. So you see this little, again, it's a little bow tie region. I don't know if you can tell, but there's this area here from pi to, now you got to figure out where they meet. And that's at 4 pi over 3. Nice thing about Desmos, right? They can tell you nicely. So you see from x equals pi to 4 pi over 3, the blue curve is on top, g is on top, and the red curve's on bottom. So I'm doing integral from, of g minus f from pi to 4 pi over 3. And then from 4 pi over 3 to 2 pi, the red curve it switches, right? Red's on top, blue's on bottom. So again, I got to figure out where they cross at 4 pi over 3 here. And then set up, break up the integrals around that value. So I'm doing these integrals here. So again, one of these is the integral from, we're going from pi to where they meet at 4 pi over 3. Again, it was the 4 times the sine of half x on top minus 4 times the sine of a quarter x on bottom. And now you can make substitutions and whatnot here if you don't like the half x, quarter x, but I'll just leave it because it's just a constant multiple of x inside, so that should be easy to take care of. So antiderivative, again, this would be, remember, it's negative cosine, antiderivative of x over 2. Remember, when I take the derivative of this, I'd be then multiplying by a half, so I gotta divide by half to make up for that, or times 2, so this would be negative 8, right? 4 times 2. Again, take the derivative of this, it'll be positive sine of x over 2, and then, again, times the half, which would make that a positive 4. Same thing here, this would be, now this was already negative 4, so plus 8 times the cosine, oh, sorry, times 4, so 16. Right, this is divided by 4, so I would multiply by 4 to undo that. So 16 times the cosine of x divided by 4. And again, take the derivative of this just to double check, right? It would be negative 16 sine of x over 4, but then times a quarter would make that negative 4. Good. And we're going from pi to, 4 pi over 3. Now, when I plug in 4 pi over 3 to these, now the cosine of half that will be 2 pi over 3. Cosine of 2 pi over 3 is negative half. So it's negative 8 times negative half. That's positive 4. And then a quarter of this would just be pi over 3. And the cosine of pi over 3 was positive half. So this would be plus 8. So the value at 4 pi over 3 is 12. And then minus, and the value at pi, now the cosine of pi over 2 was 0. So this is 0. And the cosine of pi over 4 was that square root of 2 over 2. So this is times 16. That'd be 8 root 2. So we're getting 12 minus 8 times the square root of 2, which is a positive value. You can check this. So this isn't the answer. This is just area number 1. And then we're going to add to that the integral from 4 pi over 3 to 2 pi, right, for the other one. Right, where again we're going to add to this the integral from 4 where they met, 4 pi over 3 to 2 pi of, and then the other way around. So everything's just going to be opposite pretty much here, and then I'll plug in the values. So going to be a 4 sine of x over 4 was on top now, minus, and then 4 times the sine of x over 2 was on the bottom. So again, the antiderivative will just be the opposite of what I had earlier. So you'd have 8, positive 8 cosine of half x, and then minus 16 times the cosine of a quarter x. And we're going from, 4 pi over 3 to 2 pi. Now when I plug in 2 pi, cosine of pi, remember, is negative 1. So it's negative 8. 8 times cosine of pi is negative 1. So that's negative 8. Then the cosine of pi over 2, remember 2 pi over 4 would be pi over 2 is 0. So you get negative 8 there, minus, and then I already plugged in 4 pi over 3 earlier. That gave me the, when I plugged in 4 pi over 3 earlier, it gave me 12. So remember, this is the opposite of that, the other order, so it'd be negative 12. And negative 8, minus negative 12, that's negative 8 plus 12, that'd be just 4 square units. When I plug in 2 pi, not done yet. Oh, no, I am done. Plus 4. And then 12 minus 8 root 2, there's a2. So 12 minus 8 root 2, that was the area from pi to 4 pi over 3. And then from 4 pi over 3 to 2 pi, ended up with 4 square units there. So add those together, you get 16, right? 12 and 4 minus 8 times the square root of 2. And there's your total area, and that's what I'll be entering. And again, you can check the integrals with Desmos and all that, but I'm pretty confident that I did that right. I did that correctly. Yeah, actually square root symbol here. So 16 minus 8 root 2. Okay, again, there's your picture. Again, the little bow tie region where it crosses at 4 pi over 3 here. So there's another one with some trig functions. So once again, all of the graphs of these. So one's negative sine of half x. The other one's negative sine x. I'm just going to change these here. I already have f and g in. So one's negative sine of x over 2. And the other one, g of x, just negative sine x. And we're going from negative pi to negative pi over 2. So from x equals negative pi to negative pi over 2. All right. That's between these two lines. So again, you see this, again, another little bow tie region. So let's see where they meet. So they meet at negative 2 pi over 3. So I'm going to go from negative pi to negative 2 pi over 3. with red minus blue, right? F minus G. And then from negative 2 pi over 3 to negative pi over 2 of blue minus red, right? Or, G minus F. So let's set that up. So again, the first area, integral from negative pi to where they met at negative 2 pi over 3. And in that region, again, the red was on top, blue was on bottom, which was F on top, G on bottom. So I'm doing F minus G here. The negative sine of half x, x over 2, minus, and then, G is on bottom, this negative sine x. That all with respect to x. So that's just plus sine x this, right? Plus sine x. All right, so we do antiderivative. So again, this will be cosine of x over 2, but then times 2 to make up for that over 2 part, right? So again, take the derivative of this. It should be this negative sine of half x. And then here, it's just the antiderivative of sine, which was negative cosine. We're going from negative pi to negative 2 pi over 3 here. So remember, I plug in the upper limit first. So negative 2 pi over 3. Now the cosine, now half of that's negative pi over 3. Remember, cosine's even, so the cosine of negative pi over 3 is exactly the same as the cosine of pi over 3, which is a half. Times 2 is 1. And then, minus cosine of 2 pi over 3, or negative 2 pi over 3, same thing, right, with an even function. Remember, cosine of that was negative half, so minus negative half, that'd be plus a half. So that's 3 halves put together. So there's the value at the top limit, minus, and the value at negative pi, and the cosine of negative pi over 2 is 0. And then the cosine of negative pi is, negative 1. So it'd be minus negative 1 or plus 1. So you got 1. So 3 halves minus 1, that's a half. All right, so the area, that first area between, x equals negative pi and x equals negative 2 pi over 3 is a half a square unit, positive half. And then we're going to add to that the integral from negative 2 pi over 3 to negative pi over 2 at the right end there. And it switched the order, right? So it was negative sine x on top minus this negative sine of half x, that'd be plus sine of half x on the bottom. And again, everything just turns out to be the opposite here with the antiderivative. So that's going to be, positive cosine x, and then minus 2 times the cosine of half x. And then we're going from, negative 2 pi over 3 to negative pi over 2. All right, so when I plug in negative pi over 2, right, cosine of that 0, and then cosine of negative pi over 4 was root 2 over 2 times 2, so that'd be negative root 2 at the upper limit. And then at the lower limit, minus. And we already found the value at negative, that was positive 3 halves earlier, so it could be negative 3 halves, right? Everything's switched order. And that'll be, 3 halves minus root 2, positive 3 halves minus the square root of 2, which is positive, right? This is 1.5, this is about 1.4 something. And then putting these together, 1 half plus 3 halves, well, that's 4 halves, that's 2. Altogether, this is 2 minus the square root of 2 when you put them both together. So back in the problem. So the area in question, 2 minus square root of 2. Okay, so again, they show you a little bow tie picture there, like you saw in Desmos. Again, I didn't shade anything, but figure out where they meet, figure out where they cross. All right, so this is pretty similar, where you got to pay attention to the words bounded above and bounded below. So again, if I look at these two graphs, I'll just draw them in Desmos here. So again, f of x was the square root of x plus 5 inside. G of x is some line, 1 minus x. Now, they said it was bounded above by these two curves, so red on top, blue on top, and then the x-axis, y equals 0 on the bottom. So this red here to where they meet, see they meet at -1, x equals -1, and then, the left end is at -5, 0, right end at 1, 0, and this area in between all this little, it's like a triangle, but it's not a triangle. But you see at -1, from -5 to -1, red's on top, green's on bottom. So it's just the area under the red curve to the x-axis, simple integral. And then from -1 to 1, you just have this triangle, right, with the blue on top, green on bottom. And that's a triangle with, a height of 2 and a base of 2 as well. So this would be half of 4. This is 2 square units. So I just need the area under the red curve to the x-axis, and then I'm going to add 2, right, the area of the triangle to the right of x equals -1. So we're going to integrate from -5 to -1 of just the the area under this square root of x plus 5 curve, and then add the area of the triangle, which was 2. So the total area is going to be the integral from -5 to -1 of the square root of x plus 5. And then plus, 2. Again, this was just the area of that triangle under the blue curve. All right, so remember this is x plus 5 to the half power, so my antiderivative is going to be x plus 5 to the 3 halves, times 2/3. I'll just pull the 2/3 out here. And we'll evaluate this from -5 to -1. So this is 2/3 times, now the value of this at -1, well, -1 plus 5 is 4. 4 to the 3 halves is 8. And then the value of this is -5 is 0. So this is 2/3 times 8. This is 16/3 total for that first area. And then we're adding 2, right, which is 6/3. So total 22/3. Which I guess I could have entered those integrals and gotten some nice rational value. Right, 22/3 is a nice rational number. Cool. So again, those two on top, x-axis bounded below by the x-axis. See how it's, again, it switches at -1 here. You had to set up the two integrals, two different areas. All right. All right, so again, I'm just going to do these in Desmos. So we got f is some line. And you should set them equal to each other, figure out where they meet. But it was just -x minus 3. There's f. G -x squared minus x plus 6. And from over the interval from -4 to -2. So again, I'll put x equals -4 to x equals -2. All right, so between the purple line and black line, these vertical lines that just showed up. Okay. So again, you're probably seeing that, this bow tie region, right? The you have red over blue here, then they meet at the point -3, 0, and then you have blue over red. And so I'm integrating from -4 to -3 first, do red minus blue, and then from -3 to -2, blue minus red. And honestly, since these are polynomials and these are nice rational numbers, these will end up being totally rational. So I'm just going to set those up here. So we got integral. So again, the integral from, I said from -4 to where they meet, -3. So again, from -4 to -3 of, and it was, red minus blue, red on top, blue on bottom. So f minus g, and I already have f of x and g of x typed in. So I just do f of x minus g of x dx, and then add to that the integral from -3 to -2 of the other way around, right? G minus F. So this is a 6. Now something else you could do is do the integral of the absolute value of the difference of these two functions over this interval. So watch, you got the integral from, -4, just -4 to -2 of the absolute value, which you just type in ABS of F minus G. And that kind of implies that you're figuring out where they cross and adding up the total area, right? You might have seen that before with total area, absolute value of your integrand. So that'd be a quicker way of doing that. Because again, what it does automatically is it kind of breaks it up at the places where it switches, right? It would break it up at x equals -3 like I did in the previous line. So you can do the absolute value of F minus G and integrate over just the interval in general from -4 to -2. Either way we do it though, we got 6 units there, 6 square units for the total area. Wonderful. All right, so again, that little bow tie region. All right, so now these last two, all right, so those two there were the area of compound regions, right, where I had to figure out where two curves met and then, split it up there. So these last two, so far, every function, the y coordinate has been a function of the x coordinate. So in these last two, you got area between curves for functions of y. All right. So let me describe that to you. So instead of the y coordinate being a function of the x coordinate, right? So every x gives me one y. Now we'll say, let's find the area between curves with respect to the x-axis. Right? They would call that with respect to the y-axis. All the ones we were doing before were with respect to the x-axis, right? Where y was a function of x. So now I'm doing area with respect to the y-axis. Okay, so you have x is a function of y. So say x is equal to f of y and x is equal to g of y over an interval on the y-axis. So say this is, now they're using c to d for some reason instead of a to b. So look, x horizontal, y, now we're looking at the y-axis. So, and from y equals c to y equals d. And for every y value, there's an x value. X is some function of y. Now, instead of top and bottom, like we saw with the x-axis, when I had an interval on the x-axis, we're going to have a right curve. So again, this is x equals, say, f of y, a curve that's furthest to the right, and then another curve that's furthest to the left. So say this is x equals g of y. So you see for every y value, you get 1x. Every y value, you get 1x. That's why they're saying, x is a function of y, right? These are not functions of x, right? They don't pass the vertical line test, but they are functions of y. They pass the horizontal line test. And so, in this area between the curves here, again, from C to D, would be from here up to, when y equals D. So this is my region R. So it's really no different a setup. It's just you're going to do right minus left instead of top minus bottom. So I would break this interval up into, n pieces, right? There's n pieces, n subintervals here. But each one would have a delta y height now, right? A height of delta y, some change in y, and this delta y will be the length of this interval, which is d minus c, top minus bottom, divided by, n, the number of pieces I want to break it up into. This value, the lowest value here would be called y sub 0. The highest value would be called y sub n. All very usual, all very, very much like when we were doing it with the x-axis. And then in the ith, subinterval, the ith piece that I broke this interval up into, again, would be from y sub I minus 1 to y sub I. I pick, yi star, right? All very familiar. So say in this interval here, pick, yi star, and then plug it into my functions of y here, and I get the x, this x coordinate. So the x on the left, right? We'll call this x left. And then on the other curve, we get, this x coordinate. All right, this point with this x coordinate, x right. And create a little rectangle with a height of delta y, and that is the width to estimate the area between the curves, right? And then we would do that for every single piece and add them up. So again, the area of R would end up being, the limit as n goes to infinity of the sums of these areas, right? The first rectangle up to the nth rectangle, and it's, the width across, which again is which here would be f of y minus g of y, right? The x coordinate of points on the right curve minus the x coordinate, I guess yi star on the left curve, right? X to the right minus x to the left, that gives me the distance between these, the width of the rectangle here. So it'd be f at yi star minus g at yi star, and then times delta y, right? The change in y, the height of these rectangles are all this delta y. Well, if I have n go to infinity, right? Hopefully, again, this looks familiar. This is your setup for a definite integral. This would just be the definite integral from, we're doing this from y equals c to d of, and then, f of y minus g of y dy. All right, it's all with respect to the y coordinate, y axis, right? But again, this is the right curve, right? The x coordinates of the right curve in terms of y minus, and then the x coordinates of the left curve in terms of y. So instead of top minus bottom, it'll be right minus left. Look at right minus left and get everything, everything in terms of y. So very, 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 very similar. So look, let's go back to our problem. All right, so the first one we're seeing here. So it says determine the area of the region between two curves defined by algebraic functions, integrating with respect to the the dependent variable, which is typically y, right? The y variable, y-axis. So look, I'm given these two functions. Now they're calling them u and v instead of f and g like I did earlier. So I got u of y is y plus 6. So again, you see how when y is -1, x is 5, right? When y is -1, x is 5, and when y is -4, x is 2, right? The number 2 for that u curve. And then v of y is y squared plus 6y plus 10. That'd be a parabola opening to the right, this red curve here. So they're asking us to, find the area of this region between them. So again, we're integrating with respect to the y-axis now. So look, the lowest y value here is -4. Highest one in this region is where they meet over here at -1. So I'll be integrating from -4 to -1. And again, it's the x to the right minus the x to the left in terms of y. So that'd be u of y minus v of y, the blue curve minus the red curve. So I'll set that up. Right? And then you really treat the integrals once you set them up like you did when they were x. Right, so in that picture there, that area is the integral from -4 to -1. I think it was the x to the right, which was the line. So that was u of y, the y plus 6, minus, and then the x coordinates of points on the left curve, which was the parabola which had the, v of y, which was y squared plus 6y plus 10. And again, times, dy. Now, like I said before, if you accidentally mess this up, if you swap the order of these, you're just going to get a negative value. Just make it positive, right? Just make it positive. That'll be the same. It has the same magnitude as the area between the curves. So I'm going to distribute this negative here. We'll get some stuff together. So we got the integral from -4 to -1. You'd have negative y squared. I'm just going to put the lead term first, highest power to lowest power. Then minus 6y plus y here. There'd be minus 5y. And then you got minus 10, 6 minus 10 for -4. And it's just a simple polynomial one. Again, doesn't matter if these are all x or y or t's, right? You just treat it like normal. As long as the variable of integration in the differential is the same as the variable the expression depends upon, you treat it like you normally would. Go term by term, use the power rule here. So this would be -1/3 y cubed minus 5 halves y squared minus 4y. We're going, -4 to -1. Now when I plug in -1, that's 1/3 minus 5 halves plus 4, and then minus, and then when I plug in -4, that'd be a 64/3 and 16, well, 16/2 is 8, so minus 40, and then plus 16. And you can distribute this negative here, and we can get some stuff together. Now, -40 plus 16, that's -24. But we're subtracting that, so that'll be 4 plus 24, that's 28. And then I got 1/3 minus 64/3, that'd be -63/3, which is -21. And that really takes care of this, and this, and this, and this, and this. And then I got minus 5 halves still out front here. So this is 7 minus 5 halves. That's 14 halves minus 5 halves for 9 halves. All right. So 4.5, 9 halves should be the area. And again, if you swap the order of that, you would have ended up with -9 halves. Just make it positive. Talking about area here. So yeah, 9 halves square units. You can check it with of course, again, you can check your definite integrals with Desmos and whatnot. Yeah, so yeah, it says right minus left now, right minus left. All right, so here's another picture. So yeah, integrating with respect to the y-axis now. Now, if I was doing with respect to the x-axis, remember I'm doing top minus bottom. No, it's just a triangle. I don't know why we need to do this. This is just a big triangle, right? These are lines. This is a big triangle with a base of 12 and a height of 3. So this area is half of 12 times 3, 6 times 3, 18 square units. That's, but still, if I was setting up integrals with respect to the x-axis, I'd have to switch it at 0, because you see the top curve changes at 0. But with respect to the y-axis, the lowest y value is 0, the highest is 3. I'd be integrating from 0 to 3, and then the right curve is always u, and the left curve is always v. So I would do u minus v, integrate from 0 to 3. But these are just lines in area of a triangle. This whole area put together is 18 square units. That's silly. So they set it up right with the integral from 0 to 3 of the right curve minus the left curve, right? The x coordinates on the right in terms of y minus the x coordinates on the left in terms of y, and got the same thing. But it was just nice because it was one integral and not two if you were doing it with respect to the x-axis. So again, in terms of y, all right, so you see here, again, if I was doing with respect to the x-axis, I'd go from -5 to 2, and then from 2 to 3, because the top curve changes, right? The bottom curve is always the same. But when I do with respect to y, you're going 0 to 3, right? The highest y value here is 3. I'd integrate from 0 to 3. Now I just need to figure out the x-coordinate on this right curve here in terms of y, and then, subtract the x-coordinate on the left curve in terms of y. So we got to get these things in terms of y. Now it says do not evaluate the integral. Wow. All right. So look, here are the functions we're given. Now I'm going to put y equals, right? Because we're trying to get these things in terms of x in terms of y instead of y in terms of x. So one of these functions was f of x equals x squared minus 8x plus 15. So again, this is the same thing as y equals x squared. Y is a function of x. So I'm going to solve this for x. Now let's get, complete the square here. This is x squared minus 8x. I would add 16 to this. So really I just need to add 1. So I'm going to add 1, subtract 1. So we got plus 16 minus 1. Then this is x minus 4 squared minus 1 equals y. Add the y. So x minus 4 squared equals y plus 1. So then x minus 4 is either positive or negative, square root of y plus 1, and then we add 4. Now, one of these is correct for the piece of curve I want. So x equals, 4 plus the square root of y minus 1, or x equals 4 minus the square root of y minus 1, or sorry, y plus 1. Now, let's think about the graph of this, right? So again, this has the vertex 4, -1, and it looked like this, right? You got and there was this curve here, whoosh, whoosh, right? So you see on this part of the curve, the x coordinates are greater than 4. So that would be this curve here. But the one we wanted was the left side. Right on this part of the curve, the x coordinates are smaller than 4, and that would be this one with 4 minus something positive, right? So this is our function of y on the right curve. So again, back on the picture. So you see this area, this region. So this piece of curve here on the parabola, when I got x in terms of y, this is x equals 4 minus the square root of y plus 1. Every x coordinate on this blue part here on the right curve is 4 minus the square root of the y coordinate plus 1. The other one should be easier because it's just a line, right? Solving for x on that should be a little easier. All right, the other curve was, g of x equals, it was just, 3x over 7 plus 15 over 7. So again, call this y and solve for x. Multiply everything by 7, so you got 7y equals 3x plus 15. So then x would be, 7y minus 15 divided by 3, 7/3 x minus 5. So again, that's the x coordinates on this red graph on the left side of the curve. This entire red graph, the x coordinate is 7/3 x, or sorry, the y. I wanted to solve for y. 7/3 y. My apologies. All right, I had 7y over here, so this would be 7y minus 5. So again, so on the line, all right, again, on this red line, the x coordinate is 7/3 y minus 5. So remember, this is my right curve. This x equals, oops, sorry. This is my right curve. I got the arrow here. And then this is my left curve in that region. So I'd be doing the integral from, and then again, look at the y-axis. The lowest y in this region is 0. Highest y in the region goes all the way up to 3 here where the two meet. So I'd be integrating from 0 to 3 of, and then my right curve minus my left curve in terms of y, this 4 minus the square root of y plus 1 on the right, minus, and then the x coordinate on the left curve in terms of y was this 7/3 y minus 5, and again times dy with respect to y. Now if you want to simplify things, distribute this, and then this would be 4 plus 5, so you'd have 9 minus this square root, and then minus 7/3 y. And that's what they want us to enter, right? They want us to fill in this integral. I'm integrating from, as I said, y equals 0 to y equals 3. And then this integrand, after simplifying a little bit, was 9 minus, the square root of y plus 1. And then after that, minus 7/3 y, or 7y over 3. And that should be good to fill in the integrand there. So yeah, real tricky, that one, with especially with the solving for y in the quadratic. That might be something you haven't done too much of. So again, they do the completing the square thing, right? All right, so this is pretty similar, but you have to actually have to find the area. Again, I think it'd be easier to do it with respect to x, because you just find the area under f from 4 to 5, and then there's a triangle there with a base 1, height 3. So me personally, I would just do this with respect to x, but let's still set this up with respect to y. So again, the curve on the right would be the line, all right? So from G here, so x would be, y minus 18 divided by 3. And then this, I'd have to, again, add 1, subtract 1 to get x minus 3 squared minus 1. So it'd be 3 plus or minus the square root of y plus 1. But it's the one with the plus this time, because, the curve, my left curve here is on the right half of the parabola where the x coordinates are greater than 3. So on this, it would be x equals 3 plus the square root of y plus 1. All right, so I'm taking, so, but this won't be nice. Yeah, we'll be integrating from 0 to 3. All right, so I'll write that out, though. I'll write that out, because it won't be a nice number. So if I go to Desmos and whatnot, they're going to they ask me for an exact answer, right? They don't want me to round anything. Yeah. So again, the y coordinates go from 0 to 3 in that region. So from y equals 0 to y equals 3. So again, the red curve, the g of x was, again, g of x was 18 minus 3x. So x would be y minus 18, divided by negative 3. So negative 1/3 y plus 6. So that's my right curve. And then the other one, again, was f of x equals y equals x squared minus 6x plus 8, which again is just x minus 3 squared minus 1. So I would add 1, square root, add 3, y would be equal to 3, and then again 3 plus or minus the square root, but we're on the part of the curve with x coordinates, sorry, x equals, I want to solve for x. We're on part of the curve with x coordinates greater than 3, so it would be the 3 plus the square root of y plus 1. And that's my left curve. So right minus left, I got the negative 1/3 y plus 6 minus, and then my left curve here, 3 plus the square root of y plus 1, or y plus 1 to the half power, again with respect to y. So now it's just the one integral setup, right? I didn't have to break it up into two as if I were doing the x coordinate with respect to the x-axis. After distributing this negative here, we'd have negative 1/3 y plus 6 minus 3, so plus 3, and then minus this, I'll put it as y plus 1 to the half power. All right, so antiderivative be negative 1/6 y squared plus 3y, and then minus 2/3 times y plus 1 to the 3/2, and then we're going from 0 to 3. Now when I plug in 3, that's 9 over 6, negative 9 over 6, so negative 3/2 from there, plus 9, 3 times 3, and then 3 plus 1 is 4, 4 to the 3/2 is 8, so that's minus 16/3. All right, and then minus, and then I plug in 0, that turns these into 0, and this is just 1 to any power, so this is negative 2/3 here. So that's plus 2/3, negative 16/3 plus 2/3 would be negative 14/3. So I got negative 3/2 plus 9, and then minus 14/3. And I'm just going to type this in. I know I can get everything over 6, but just going to type that in. That'll be correct. So this area should be negative 3/2 plus 9 minus 14/3. That should be equivalent to what they have. Wonderful. Yeah, 17/6 when you get it all together. So once again, we're just setting up an integral, not evaluating it, right? So just fill it in. Now the nice thing about this is they give us the functions in terms of y, right? They give us the x equals square root of y plus 3, x equals, y plus 3 over 4. And the red curve, the u function is on the right, v is on the left. And the y coordinates go from negative 3 on the bottom to 13 on the top. So my limits would be negative 3 to 13, and I'd be integrating, my integram would be u minus v. So this square root of y plus 3 minus this y plus 3 over 4. So I'll fill all that stuff in. So again, from negative 3 on the lower limit, it was up to positive 13, right, for the upper limit. Yeah. And then the integrand, that square root of y plus 3 was the x coordinate on the right curve, then minus, and then this quantity, the x coordinate on the left curve was this y plus 3 over 4, the v function. So again, the y plus 3 over 4. That should be good. Don't find it, right? Just plug the stuff in. All right, so this one, find the area. They actually want it. Nice thing again, though, is they actually give us x in terms of y. They give us the functions of y here. We don't have to solve for x and get x in terms of y. All right, so this time, now u is on the right, v is on the left. And the lowest y here is negative 2. The highest is 14. So here's the integral I'm going to set up. Again, u on the right, v on the left. So here's what they gave me. So we're integrating from, lowest y was negative 2, highest y was 14. So from negative 2 to 14. And the x coordinate on the right curve in terms of y was 4 times, now it was the square root of y plus 2. So again, I'm going to write that as y plus 2 to the half power. Minus, and then the x coordinate on the left curve in terms of y is just y plus 2. That was the v of y. And I can distribute this here. And, well, don't really need to. So let's do antiderivative now. So again, this would end up being just y plus 2 to the 3/2, times 2/3, but I had 4 there as well, so that's 8/3. Minus, and then half of this y plus 2. And I'm only doing this because, y has a coefficient of 1 here, so I just keep it together. This y plus 2 squared, half y plus 2 squared. And we're going from negative 2 to 14. Now, when I plug in 14, Oh, this ends up being nice, actually. When I plug in 14, this is 16 to the 3 halves, which is 64, right? Square root of 16 is 4, cube is 64. And, 8 times 64 is 512, so this is 512 thirds minus, and then 16 squared. 16 times 16, but half of 16 is 8. That's 8 times 16, 80, 80, 80 and 48. That's 128 minus 128. And then when I plug in -2, they're both 0. So I'm just going to type this in. All right, 256. Yeah, cut in half, 128. And just one more check real quick. Yeah, that's 4 cubed, 64 times 8, 480 and 32. Yeah, so that's going to be the correct area. So again, without putting them together, I don't really feel like it. 512 over 3 minus 128. That's how many square units should be in that region. Great. All right, then I find the region again, right? Area. Now this is another one where they give us the functions in terms of x. We have to solve for x, get x in terms of y. And you see, like if I was doing the integral with respect to x, I'd have to go from 3 to 4, and then change it, and then go from 4 to 5 because the top minus bottom changes, the curve on top changes. But with respect to the y-axis, right, I'm going from 0 to 1, and the right curve's always the same, the left curve's always the same. So I just need to take f here on the right, get x in terms of y, and then take g, which is on the left, and get x in terms of y, and then set up the integral from 0 to 1. All right. So let's solve those. So f of x is 5 minus x to the 6/5 power. So again, you call that y. I would raise both sides to the 5/6 power. And then swap the, add x, subtract this. So x equals 5 minus y to the 5/6 power. And this was the curve on the right. This was the right curve in my region. And then the other one, g, was the curve on the left. All right, g of x is given as x minus 3 to the 5/6 power. So again, I would call this y for g of x here, the output y. Raise both sides to the 6/5 power. Then we got x minus 3, and then just add 3. So x equals 3 plus y to the 6/5. There's the left curve. And again, I said the area will be the integral from 0 to 1. And it's always, right minus left. So when I subtract these, take this minus these, 5 minus 3, that'll give me 2. And I got minus y to the 5/6, and then minus y to the 6/5 dy. That's what this is the expression I get when I take right minus left, this expression minus that one. All right, antiderivative, right, 2y. Now add 1 to this, it'll be plus, it'll be y to the 11/6. So then times 6/11, so minus 6/11, y to the 11/6. Minus, and then this, I would add 5/5, right, to add 1. So that'd be 11/5 times 5/11. And we're going, 0 to 1. Now, the nice thing is when you plug in 0 for y, it's all gone. So this is just going to be the value at 1. So 2 minus 6/11 minus 5/11. So this is 1, right? Because that's minus 11/11. 2 minus 1. How nice. So that area there is just 1 square unit. Okay, it's pretty similar. Yeah. Here, again, f is the right curve, g is the left curve. We integrate from 0 to 1 again on the y-axis. So x would be y to the 7/8. It would be 8 minus y to the 7/8. And here x would be 6 plus y to the 8/7. I subtract those, and you would get 2 minus y to the 7/8 minus y to the 8/7. I think that there's going to be 1 again. Let me write it out just to be doubly sure. So again, the right curve would be x equals 8 minus y to the 7/8. This is the right curve. Left curve, where the x coordinates in terms of y would be x equals 6 plus y to the 8/7. And you're subtracting all that, right? Just the stuff with y though. So we're doing the integral from 0 to 1. Again, 8 minus 6 is 2 again. You got minus y to the 7/8, minus y to the 8/7 dy. Do some power rule stuff. This would be 2y minus, I would add 8/8. So that'd be 15/8. Y to the 15/8 times 8/15. Yeah, this is 1 again. Very, very similar to the last one. Then this one I would add 7/7 for, y to the 15/7 times 7/15, and we're going from, 0 to 1 on the y-axis. Again, the value at 0 is 0. So I'm just getting the value at 1 minus 0. The value at 1 would be 2 minus 8/15 minus 7/15, which is again minus 15/15. So this is 1 again. All right. Very, very similar to the last one. Area is 1 square unit. Great. All right, and that's it. So pretty long one there. A good 2.5 hours. A lot of just finding areas of regions, right? And when you're doing things with respect to the x-axis, doing it over some interval on the x-axis, your integrand should be, top minus bottom, top function of x minus bottom function of x. And when you're integrating with respect to the y-axis, right, over some interval on the y-axis, your integrand should be, right function of y minus left function of y. And that's it. All right, and just make sure you understand where they cross, where they switch. You might have to worry about that. And yeah, hopefully watching me go through all these here help you out in some way when you work on it yourself. Thank you very much for watching.